Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, today it's my pleasure to welcome Peter Dollar here to join us to give a talk on pedestrian detection. He recently graduated from UCSD and is currently doing a postdoc at Caltech, and he'll be describing his work that he's presenting at BMVC today.
Yeah, just a general overview.
Okay, great.
Cool. Well, thank you for the introduction, and it's great to be here. So today I'm going to be talking about pedestrian detection, the state of the art. So I'm going to give a sort of an overview of what the state of the art is, and then talk about our own work and our own detection system and sort of the advances we made there recently. So first of all, let me say, why am I studying pedestrian detection? Why am I interested in this problem? Well, I mean, as many of you know here, it just has a large number of really compelling applications. Robotics, image indexing, HCI, technology for visually impaired, surveillance, automotive safety. And actually that last one is the one that sort of motivated us to work on this in the first place. But the other reason for really studying this problem is you really get to look at some fundamental problems in computer vision and machine learning. You get to really think about object detection in general, feature representations, learning paradigms, sort of specific things that actually occur when you're doing object detection, like scale, occlusion, pose, role of context. So it's just a great problem in general. So this is a problem I became interested in when I got to Caltech about 3 years ago. At the time, we were funded by an automotive company, and since then that's no longer the case, but it's a problem I've been sort of continuously interested in. And my work has been in sort of three areas. One is sort of benchmarking and figuring out actually what works, what are the common elements, sort of evaluating the state of the art. There's been a lot of claims, people making we have this amazing detector, and really seeing how those claims hold up, in what conditions. And so we learned a lot through that. And so the first part of the talk, I hope to be able to communicate some of that knowledge to you. In the second part of the talk, I'm going to be talking about our own detector. And so one of the first things we did after sort of doing this evaluation is we really had a good sense of what the key components of a detection system were. And so we were able to put together basically a very simple system that sort of really boiled down what's required to have a good detector. And it actually performs really well. It's something at the time that we published it was something like a 10-fold decrease in false positive over any competing method. And since then, others have caught up, but it's still one of the best systems. And actually, I'm going to give a fairly brief overview of the system and then really dive into sort of a recent insight we've had that's allowed us to speed up the detection by a factor of 10 over our previous method and 10 to 100 over competing methods. And it's really something that's pretty general and should be applicable to anyone sort of doing multiscale detection. So that'll be sort of the main technical component of the talk. I've also been very interested in sort of the learning paradigms you use for detection. So part-based methods and setting that up as a learning problem where you don't have to have full supervision. But I won't actually talk about that too much today for lack of time, but if anyone's interested, that's something I'd be very happy to talk about afterwards. So the first part, I'm going to do this overview. What is the state of the art in pedestrian detection? So what we did, one of the first things we did at Caltech, and this is joint work with Christian Voyek and Bernd Schiele, was we went out and we gathered this huge data set of pedestrians. And so we a fairly standard setup where we had a camera hooked up to a vehicle, a 640 by 480 VGA camera. And we had somebody drive around, and wasn't a computer vision researcher, so hopefully they weren't biased in any way. Had him drive around and record video of the car, and then we went ahead and we labeled a very large quantity of video. So we have something like 1/3 of a million bounding boxes labeled. So that's really a big number. I mean, think about that number, 300,000 people with boxes around them. Now, of course, many times it's the same person. There's only about 2,300 unique individuals that are labeled, but they're still labeled for a long time. And of course, we didn't do this ourselves. We hired some people to do it. Most of them would flake out after maybe doing this task for 4 or 5 hours. But then we had the wife of a postdoc in our lab who really stuck with this, and I think she did something like 350 hours of labeling. And she said she couldn't sit in a car and look out the window because she'd be drawing boxes around people in her head. So, yeah, not a fun task. I wouldn't recommend it. But yeah, it did give us this really incredible data set. And then I should just say, and so the data set's available online. I sort of have this link up here the whole time, and this is sort of the data set. And all the stuff I'm going to be talking about is available online, evaluation code, and so on. Including this, so we had this annotation tool. So still, even if we hire somebody for 400 hours, if we were to just label individual frames one at a time, it wouldn't be really a feasible way of labeling. So we have this tool where you label the person one frame and then label them 50 frames later. It tries to do some interpolation. It doesn't use any of the image data to do interpolation. We tried to use a tracker and other techniques for doing the interpolation, but we found that from a user's perspective, it was actually better to do something that's very predictable. So it ended up being just a very simple cubic interpolation. And then the user goes in and fixes those where it's still making a mistake or reinterpolates, and you do this a couple times until you have good tracks. So this sort of makes it feasible to label large quantities of videos. Of course, the drawback is that you're labeling a huge number of frames, but the drawback is that frame to frame, person may not change that much, the visual appearance. So that's sort of the trade-off. So I want to say a little bit about the sort of the statistics and what we learned about about pedestrian detection in the real world. So we did some statistics of the height of people. And so here on this graph on the left on the x-axis is the pedestrian height in pixels. It's in log scale, so they're log-sized bins. This is sort of the distribution of the size of people. So again, this was a 640 by 480 camera, and so this is going to be very application dependent. But nevertheless, we found that, and that was sort of that was the setting that the automobile company that we were working with was pushing us to use. They really didn't want us to use high resolution cameras, which I disagree with that approach. But that was a constraint they gave us. And anyway, under these settings, when you have the 640 by 480 VGA camera, most people are between 32 and 64 pixels high. And then sometimes you get bigger people, but of course, if there's a person right in front of your car, maybe that's not ideal. So hopefully you don't have people right on your windshield. And then below 32 pixels, there's actually not a lot of people either, because that's sort of the resolution limit in this quality of video below which you really can't see people. And so the other thing here is from a safety perspective, let's say you're driving around 55 kilometers per hour, so maybe a little fast for city driving, but reasonable. And you make some assumptions about the height of people, but the size of a person is inversely proportional to the distance from the vehicle. And so here you have the distance, and here you have the height in pixels. So yeah, as the distance increases, this blue curve, this is the perceived height. And so basically what happens is if a person's 60 meters from the camera, you have about 4 seconds, so you have time to react if you want to, let's say, alert the driver in whatever way. And so really that's when you want to start detecting people, and they're about 30 pixels high. By the time they're 80 pixels high, you have about 1.5 seconds to react, and bye-bye pedestrian. So you really want to warn the driver sort of when the pedestrian is a little further away. And this, I'm just using this to emphasize that really for these type of applications, you really want to be able to do detection of smaller scale pedestrians. And I should say that a lot of the work, including our own work, we had some part-based work, was focused much more on this realm of higher resolution pedestrians. And so again, this is going to be very application dependent, and I'll talk a little bit more about that. I think actually the type of techniques one would use for low resolution and high resolution vary a lot. And so I'll discuss that. But to do well on the type of data sets that are sort of out there, you really need to do better on the low res pedestrians. So the other interesting thing is, so I guess I didn't mention this before, but when we were labeling the data, we would actually label both the pedestrian, a box for where the person would be, and then another box for the visible region for the person. So every person's labeled with 2 boxes if they're occluded. So let's say you're looking at me and you're labeling me. You label one box to the ground and one box that just contains my torso. And so anytime a person was occluded, we would have that information. And so basically what you see is this is the fraction of time that a person's occluded as they're walking. So let's say you see them for on average about 150 frames, so about 5 seconds. There's some people, about 20% of people are always occluded. In fact, there's only about 30% that are never occluded. So really, if you want to do a good job, you really have to deal with occlusion. And I think this is something that, for example, when one is using the intermediate pedestrian data set, which is sort of the data set established by Dalal and Triggs, that's sort of been used heavily for pedestrian detection, there's really very little occlusion or no occlusion in the data they labeled, they selected it. And that's really not realistic. On the other hand, occlusion isn't random. So what we did is here on the right is we have all these sort of masks, right? We have the box containing the pedestrian. We have another box containing the visible region. So you can kind of create a binary mask, standardize the size, and you can average all of those together. So you get a heat map of which portion of a person is typically visible. Okay? And so basically what you get actually is that, so this is the head region. The blue indicates that it's rarely occluded. Red means it's often occluded. And so what you see is that in the real world, actually, you'll oftentimes see my head and torso and not my legs. And in fact, sort of makes sense if you think about how the real world is with gravity and whatever else. But we took this a step further, actually, and it turns out that if you cluster, if you look at actually a little more deeply at what are the types of occlusions, so you cluster these masks, and it's not so important exactly how that clustering is done, but what happens is actually, so these numbers I guess are a little hard to see, but this occlusion mask occurs 65% of the time. So 65% of the time, the occlusion is very simple. It's just the bottom part of a person. And then these other few, like this one occurs, like for left to right, occurs about 5% of the time, bottom and left another 5% of the time. But again, the lesson here is that the occlusion isn't really random. And you could really try to exploit this kind of information. It's not uniform, so which I don't know if people have. Yes?
Is this a fact about occlusion, or is it a fact about the people you manage to detect? If somebody had his head hidden away, would you detect it?
Right, and then so that's a really interesting subtlety. Right, so the question is, so you're looking at me and you see my torso, so you detect me. But let's say, I'm hiding and all you see is my legs. Would you still detect me? And that could be that's absolutely right. That could be a bias. On the other hand, so we're not doing detection just from one frame, right? We track the person over let's say 50 frames. And so odds are that, there are some people that are always occluded 20% of the time, but we still have lots and lots of people that are just occluded part of the time. And it's rarely the case that those people are ever occluded from above. But yeah, that could be a bias. So online, again, I keep flashing this URL here, but we have an evaluation of lots and lots and lots of algorithms. I think at the time, this slide has 12. I know there's at least 2 ECCV papers that are using this data set. There's 2 more algorithms that we're evaluating at this time. And so, sort of interesting. So this is log scale, and so you can kind of see that, there's some order here temporally when these were published. And so there is some progress. These curves are sort of kind of moving down slowly. But this is a log scale. So actually, from Viola-Jones to, that's even hard to say. But for a lot of these, a shift of sort of one grid cell over here is a 10-fold reduction in false positives. So even though these curves may not look like much, like let's say we can look at Hog here, which is the orange curve, and these algorithms over here, that's a 10-fold reduction in false positives. So progress is being made. Yes?
Is it miss rate or hit rate? Because it looks to me the red line never sees any pedestrians.
This red line the Viola-Jones system worked incredibly well for faces, but without some modifications, it doesn't work that well for pedestrians. So yeah, that's absolutely right. The Viola-Jones at most gets about 80% detection.
The hit rate.
Gets at most 20% detection. Yes, thank you. Thanks for keeping me honest. Yeah, and so basically what you get is, this is one particular curve. We break this down further. This is sort of the overall result. You get that about 1 false positive per image, you detect about 70% of people for the state of the art. Now, but with the caveat that this very much depends on the resolution of the people, whether you include occluded or not people. And so we have a further breakdown on the website. I won't go into too many details here. I think that, but if you're interested, all that information online. And I'll say here's our own detector, so it's the second best here. And in fact, the only one that's better also uses motion information. And so we're about, at least at the time, right now, before ECCV, we're about 10 times better using just static features than anyone else. Actually, Devaramanan has a paper at ECCV which actually beats this. But it's unpublished, so I'm not including it here. And so I'll talk about that in sort of the second part of the talk. What does all of these detectors have in common? What is sort of the key ingredients that make these detectors effective for pedestrian detection? And so all of these algorithms are pretty much sliding window algorithms. There are other approaches like Huff-based approaches, but they tend to not work unless you have much higher resolution data. All of these methods use histogram of gradients in some form or another, not necessarily HOG, but in some form. The best algorithms also integrate more feature types. So one interesting thing here is, when I was a grad student, I was very much into machine learning, and I still am. But one interesting thing here is what role does the classifier play versus the feature, which is something some people here have explored. But it turns out that, and like you guys found, that the classifier itself you use once you have a feature representation plays very little role. So whether you use boosting or SVM, or within boosting, there's Ada boost, gentle boost, logit boost, real boost, savage boost, brown boost. I could go on, right? And we've tried about 3 or 4, and if using the other system fixed, and it really makes very little difference. Now, having said that, all those classifiers that I just said, and SVMs, whether you change the kernel a little bit, it'll make a difference, but not huge. All of those are all using the same framework, where it's just a framework of binary classification. But I think the role for machine learning to sort of advance detection is where you set up the problem in a more interesting way. Like you have less supervision during training, so you allow for slop. Or you have part-based methods, or some form of latent variable that allows your classifier to be more powerful. For example, that for a single visual category, you learn a mixture model of classifiers. So I think that's really the place where we're seeing machine learning being able to play a role to advance us, and not necessarily swapping algorithm for X for algorithm Y within the same paradigm. And the last thing I wanted to say, that all of these detectors, they typically all behave the same as you change the conditions. So if you increase occlusion, all the algorithms work, both the part-based one and the monolithic ones. And the only setting under which there seem to be some differences between algorithms is low versus high resolution. And I'll talk a little bit more about that, but basically you have less room to be clever in terms of part-based methods and whatnot at low res. So anyway, so there's benchmarks up there. We evaluate all these different settings. And in fact, we've taken a lot of other pedestrian detection benchmarks and ran all these algorithms and all those other ones. So you really get to, if you're interested, you really can go see how well the various methods in the literature are performing. So sort of the open problems in pedestrian detection. So things work reasonably at large scale unoccluded pedestrians. Definitely not how we'd want them, but maybe okay. Where things really break down is when you have lower res or occlusion. Now, of course, there's additional sources of information you can use: context, spatial, temporal, whole system performance, motion. And people are using those, and I have some students working on that this summer. There's been a decent amount of published. Like, for example, if you know you're in a vehicle, you can exploit that information. For high-resolution pedestrians, I think that's actually maybe an area, if not for the data set I've been talking about here, but an area where there's a lot of room for improving the detection itself. But I'll talk a little bit more about that later. One final thing I wanted to say about this is sort of maybe a little bit boring, but when you're doing evaluation right is actually really important. So there's 2 ways of sort of evaluating detectors, and one is the Pascal criteria type of thing, where your detector outputs bounding boxes, and you want to do sort of the overlap with the ground truth bounding boxes, measure it that way, and I refer to that as the per image evaluation criteria. The other one is per window, so that's sort of if you're training your machine learning algorithm, you have a bunch of windows that are negative and a bunch of windows that are positive. You measure error on that. It turns out that oftentimes per window error can be very misleading, both because it's really easy to make a mistake during the valuation, and because sometimes it's not really measuring the thing you want it to be measuring. And so this is just, so these curves on the left here were taken from the literature. And so basically you had Viola-Jones, and then you had Hogg, which is this dotted orange curve, and then you had these algorithms, again this is a log scale, that are just absolutely destroying, like by a factor of hundreds of performance from Hogg. And it turns out that we went and we got these algorithms from the various authors, and it turns out that actually we ran them, and they're really not, even though the one here, this blue one, this using histogram intersection kernels, it's a little bit better than Hogg, but all these algorithms actually were not. And that was a really disappointing thing for me, that I would go into the literature, find these great algorithms, and it turns out that they're really not that great. And so I think that's happening a little less now that sort of we have these bigger data sets and people are using those. But just something to be aware of, that a lot of results that have been recently look really good. Sometimes they look just really good on paper. And if we want to understand the progress being made, we really have to do a careful job of evaluation. So a little bit of a mundane point, but important to keep in mind. Don't use this measure if at all avoidable. It's at this point not very convincing. So that, yes.
You mentioned about Viola-Jones. Did you retrain Viola-Jones using R features extracted for pedestrian boxes?
Yeah, not for faces.
So my question is, like, did you ever run the state-of-the-art face detector on your dataset and see how well it does?
Oh, I see. I mean, but the problem is at about 50 to 100 pixels. That I mean,
just for curiosity, because you say most of the occlusions have the.
Oh, I see. But you also have to remember that it's not just frontal faces, right? Sometimes
face
the people are
detection is
facing.
like state-of-the-art now. It can like detect profile faces and back.
In ideal world, yes, but no, we did not run that. And I think
you have
this,
like many detectors, being like state-of-the-art detectors, just downloaded from their like off the shelf and then being run.
Yeah, so for Viola-Jones, we actually used the OpenCV, and then we had our own
maybe
implementation.
But like Takio student has like one of the latest space detectors.
Sure. I mean, so there's a question, sort of, are we actually able to test every detector in the literature? And the answer is no.
Yeah. Okay.
Yeah. So.
I was thinking face detection. How well is?
How well?
Face
Yeah. No. I
detection
mean, that's an interesting question, and we can talk about it a little more offline. But it's a reasonable question. Yeah. Yes.
This is maybe off subject, but if you talk to the military, have you considered detecting a woman wearing a burqa? Even at high resolution?
Yeah. I have not, no. Yes?
It seems like this, you could combine any output based on vision with something like a heat-seeking infrared camera.
Yeah, so there is a bit of work on, so all of the stuff I've been talking about is monocular pedestrian detection. And of course, the two other things that people use is stereo and motion, of course. Some of the detectors I was talking about use motion. But yeah, actually, what actually ends up happening is it's not as trivial to use those other sources of information as one may think. But there's definitely work on that. Yeah. Yeah, like Bernhard Horne has like a bunch of, he had some students working on using infrared, and sometimes you can do ROI detection very easily. But again, it's not a panacea as one may expect. When you get these other sensors, it makes some things easier, but it doesn't solve the problem, for sure. Okay, so that's sort of the state of the art in a very brief overview, and I'm sure I didn't do it complete justice, but. Take a look at the website, take a look at our benchmarking paper, and we're preparing a journal version of the benchmarking paper, which we'll go into a little more depth. But so now in the second part of this talk, I wanted to sort of say, so I gave kind of an overview of the methods out there. I wanted to talk about our own method. And at the first part of it, this is sort of from 3 papers, an older CVPR paper and some recent PMVC papers, one that not published yet, just found out about that it got accepted a couple days ago. But at the beginning, when I'm telling you about the system, everything should be sort of clear and be like, oh, this is very natural, this is very simple. And that's sort of the goal. We really tried to distill the system, but again, it works quite well. So what we basically did is we wanted to integrate multiple feature types in a very clean, uniform manner. And so there's this long history of using basically image channels in computer vision. So what is an image channel? You basically take an image and compute some kind of linear or nonlinear transformation of the image where the output has essentially the same dimensions as the input image. And so those could be as simple as, say, the color channels, linear filter outputs, in this case some Gabor filters, or difference of Gaussian filters, of offset Gaussian filters, something like the gradient magnitude, edge detection, gradient histograms, which are very similar to kind of Gabor filter outputs, but you basically, in each channel, you compute the gradient and you leave the gradient at a given orientation in that channel. So it's just a way of just doing integral histograms. But you can kind of think of all types of channels of this nature. And the idea was to basically in a nutshell, to take the Viola-Jones system, but run it, instead of just on grayscale images, where you compute hard features over grayscale images, and a hard feature is just a sum of a rectangle or sums of multiple rectangles computed quickly using integral images. The idea was, instead of just doing this over the original grayscale image, do it over all these different channels. And it's really a very simple idea, a very natural extension. But now you can sort of, any one of these channels that I kind of drew up here, you can kind of write that in 10, 20 lines of MATLAB code or whatever your favorite image processing toolbox is. And so then basically if you have Viola-Jones implemented, then it's pretty easy to integrate those features into an overall system. And so, like I said, there's very few parameters. It gives you very good performance, fast to compute. But the key thing here is this integration of heterogeneous information. Let me say a few more details about it. So initially, the features you use, these hard features, so Viola-Jones had these sort of approximating gradients. And those may make sense over the grayscale image, may not make as much sense over these other channels. So at some point we were exploring using gradient descent or some various search strategies to basically find the optimal combination of rectangles to be a useful feature. And so what we actually found, that does help, but what we actually found, and these are some of the combinations found for faces. But we found actually that use random features works quite well. And in fact, instead of even having these complex features, which are these combinations of rectangles, single rectangle random features work great. And we use these soft cascades developed here at MSR actually for the training. There's a misconception about boosting that it takes weeks to train, or the system takes about 5-10 minutes to train, say on pedestrian detection. So I think initially the Viola-Jones system was a bit slow, and part of that was because they were using a huge number of features. And we find that if you just use random features, you do some caching, like I said, training can be 5-10 minutes for one of these detectors. For the weak classifiers, we just use simple little decision trees. That's sort of necessary because your features are so simple. So here, some of the blurred channels, not so important. But so this is just I gave kind of a whirlwind overview of the system. But the point is it actually performs really well. It performs a lot better than any other detector that only relies on features computed from a single frame without motion. So this very simple distilled system can actually do quite well. Yes?
The weighted rectangle, do you have like filter weight map for each rectangle?
Yeah, so originally, so you can imagine, so Viola-Jones, let's say a typical feature they used was two pairs of rectangles next to each other, one with a +1, one with a -1, and you compute the sum of the pixels in the two and do the subtraction. But when we were doing random features and we wanted to have combinations of features, we also let the weights be random in how you weight it. So you maybe have this rectangle times 2/3 minus this rectangle times 1/4 plus this rectangle times 2. So it's just a way of creating a richer feature representation. But like I said, in the end, we ended up just using random features, and each feature is just a single rectangle, in which case you don't need weights, right? Because it's just one rectangle anyway, and boosting then assigns the weight. So yeah, but I think that sort of so far what I've talked about is a system that I think anyone could take that has worked with Viola-Jones and really extend Viola-Jones to give you state-of-the-art performance.
In practice, random features. Basically, what you do, you have initial pool of random features,
Yeah.
and then boosting does your features.
Yeah, no, absolutely. I mean, that's absolutely the key. If you were to use truly random features without any kind of selection, in this case, it wouldn't work well. Yeah.
By the way, did you see in your feature selection done by boosting, did you see any preference to certain types of feature? I mean,
Like medium-sized.
No. I mean, like he discarded certain, I don't know, keyboard features altogether.
Oh, I see. Yeah. So
Very small
this was so we ended up using just 3 channel types, which is these quantized gradient, gradient magnitude, and color channels. And this is sort of I don't want to go into too much detail, but this is sort of visualization of where the features were picked. And so, for example, for these gradient magnitude, so this is let's say the vertical gradient magnitude, and like to have a lot of vertical gradient magnitude in these regions. For, let's say, the LUV color channels, so for some reason LUV worked really well, and in fact, it really likes the features around the head. So I guess it really is picking up on skin color. So this isn't exactly a face detector, but it actually implicitly is capturing that type of information. Yeah, and we've done some studies actually similar to sort of what was done in Ullman's group, where we looked at sort of the size of the features. And it turns out that basically we found a very similar thing, that if you discard very large features, you're fine. If you discard very small features, you're fine. But you do need the sort of medium-sized features. So very similar in that regard. This is just the results on the INRIA data set. This is a higher res data set. We're sort of tied for the best performance. We were doing an epsilon better, but that might be just noise with the latent SVM stuff. So typically, the system I've described, which doesn't have any notion of parts here, does better on lower res. And on higher res, it basically does as well as the state of the art. Yes?
Maybe you're going to get into this, but I was just wondering if there's some key intuition as to why the boosting with random features works better than the others. Is it like the others were over-engineering features? Or?
I mean, I wouldn't say it's just a boosting of random features. I mean, I think there's at some point it does come down to just good engineering. But I mean, one advantage we have is that we can integrate the very different feature types in a uniform way. So, a lot of systems that say just use hog or variant of hog aren't using any color. And for us, using color helped quite a bit. Of course, how do you integrate color and gradients or sort of different animals? That can be sort of tricky, but in this system, it's so sort of uniform, you don't have to think about it. Yeah, and actually, it's interesting because right now we have these 3 feature types basically, and we've tried lots and lots of others because you can kind of dream some stuff up and add it, and actually not that much stuff makes much of a difference. So these seem to capture a good chunk of the information we'd want to get. This is Pietro's vacation photo data set. I call it a data set kind of jokingly. So you can kind of use these photos to see how our detector is performing or see pictures of Pietro's family. Yeah, I mean, these are just typical results. Pietro really likes sending me these images where he thinks the detector will fail. That's sort of a game we play. He finds images where he'll trip me up, and he did a really good job with these windows here in this building in Venice. So here are some of Pietro's kids playing, and these are sort of typical false positives. Anyway, this is just sort of to give you a sense of what it's doing. But yeah, any more questions about the, yes?
Just in a real application scenario, when you're capturing the images, moving car, won't they be blurred?
Yeah, I mean, there is definitely a little bit of blurring. I mean, this data set does have that. That's one of the reasons the absolute performance numbers on this are much lower than they are on the INRIA data set, which is from still images, which do have a higher quality. So that definitely degrades your performance a bit. Yeah. So that's the overall system. And again, I mean, the key was they're sort of boiling it down to sort of the key elements. What I wanted to talk about sort of for the rest of this talk, sort of the main kind of meat of the talk, is a recent insight we had that basically allowed us to really speed these things up. And so it's actually quite interesting, and I think it's fairly general. So basically the original Viola-Jones system, the reason it was so fast is you took your image, you computed your integral image, and then when you ran multiscale classification, you could test every window, and you can test every window at every scale without it doing any feature recomputation. And so that was really, really fast because in some ways the feature computation stage, which really was just integral images, you did once and then you did multiscale detection. With sort of modern detection systems, you can no longer do that. Because let's say you're computing gradients, what you do is you train a model at a fixed scale, and then you shrink your image, and you perform detection, and you shrunk an image, and you shrink your image again, and you perform detection. And so every time you shrink your image, when you're looking for the same size detections, you're obviously looking for bigger pedestrians in the original image, right? But this becomes pretty slow because basically all that stuff I was talking about, whether it's an R system or any other of these detector systems, you have to recompute all the features for every one of these images in the pyramid. Okay? And so basically, so again, but I mean the advantage of course of this is you can use much richer features because Viola-Jones, the original system was limited to just grayscale features. So can you sort of combine the advantages of both? And we basically had an insight that you can, and it's based on sort of interesting work done in the 90s about the fractal structure of the visual world. Meaning that if you take a photograph of a scene, the statistics on average of that photograph will be independent of the physical area subsumed by a single pixel. So whether I take a picture of this room, where a pixel may correspond to a certain dimension, or I zoom in on someone nearby, like I zoom in on Larry and take a picture of his face, on average, the statistics of images taken at those two different scales will be the same. And that actually, the sort of fractal nature will allow us to approximate features at other scales. So it'll take me a little while to get there, but bear with me. Normally the reason you can do sliding window at a single scale very quickly is that your features, and omega here denotes feature computation of features, in this case gradient magnitude, are invariant to shift. So whether you translate your image and compute the features, in this case gradient magnitude, or compute the features and then shift your images, you'll get the same result. And that's ignoring sort of the boundary effects here, but this holds. So you can do this operation in either order, which means that you don't actually, when you're doing detection, you don't have to crop every single window and recompute the features in that window. You could just compute the features once for the whole image and then crop sub-windows from the feature map. And this wouldn't be true, for example, if you had smoothing of the image, where you wanted to smooth the window with more smoothing, say, towards the edges of the window than the center. Then you'd actually have to crop and recompute the features. But typically the features we work with in computer vision tend to be shift invariant. So that's why you can do single scale sliding window without recomputing features. This does not hold for scale. So let's say I have an image, I shrink it, and I compute, say, the gradient magnitude. That's not the same as computing the gradient magnitude and shrinking that result. If you think about it, I mean, a very simple example, let's say you have a checkerboard, very high frequency, white, black pixels alternating. You compute the gradient magnitude. It has lots and lots of gradient energy. You shrink that, it still has lots of gradient energy. But if you shrink the checkerboard, it's white and black pixels, you basically lose that frequency. It becomes a gray. It has no gradient. So you can't reverse the order of these operations. And so that's why you have to recompute features at every scale. Okay. Okay, I don't need to say this. So this will be my only equation-heavy slide, I promise. But it's super simple. Basically have I denotes the image, these denotes the gradients. Gradient magnitude is just at a pixel ij is just the sum of the squares of the gradients, square root. The angle, the orientation is just arctan. And then we quantize orientation to q-bins. And a gradient histogram is the gradient magnitude summed over some rectangular region at some orientation, and this was quantized. So super whirlwind introduction to gradient histograms, but hopefully this is sort of familiar to everyone. And I should say, by the way, for sort of the purposes of explaining these ideas, I'm going to be talking about gradients and gradient histograms. But these concepts will actually hold for almost any feature type, and I'll try to make that a little more precise later on. And okay, one other thing. So this is a gradient histogram. So this is the sum of the magnitude at a given orientation over a region. This is a bin of a gradient histogram. Sometimes, just for simplicity, actually, I'll be talking about the sum of the gradient magnitude at a region at all orientations. Okay, so hopefully this is okay. So I'm going to try to make this a little bit interactive. So please answer some of these questions if you can. So we'll see how this goes. So we have, let's say we have a pair of images. Or an image and an upsampled version of that image by a factor of 2. And we compute the gradient magnitude for each of those. And then we sum all the pixels in the gradient magnitude here, and we sum all the pixels in the upsampled image. What's the relation between this scalar and this scalar? I'm sorry? Close. So let me give a hint. So when you upsample an image, the gradient actually decreases, right? So if you have a sharp edge, you increase its scale, the magnitude of the gradient actually decreases, so by a factor of a half.
Equal. Constant.
All good guesses, all close. Nobody's hit it yet. It's just a factor of 2. So the gradient magnitude at each point is just 1/2, but you have 4 times as many points. Okay? And so
You're assuming you just upsample it. You're talking about the original image that has more high frequency content.
yeah, so you're not. So that'll be the more interesting case that I'll get to in a second. So in this case, sort of nothing magical is happening. When you upsample, you're not creating information. And so it makes perfect sense that you don't actually have to upsample and compute gradients to predict the gradient content of the upsampled image. Nothing really special so far. But we went ahead and so this experiment isn't going to be that interesting, but it'll lay the framework for sort of the experiments coming up. Went ahead and gathered a data set of images, computed the gradient magnitude, summed them, upsampled, performed the same operation, looked at the ratio, and then we plotted a histogram of that. So as expected, most images, when you upsample is 2, there's some noise because of, say, the interpolation procedure. And we tried a few different interpolation procedures, but typically there's always a little bit of noise. So this is basically plotting this ratio. So in fact, if you take a data set of images and do this, it's usually around 2 with some noise. And there's 2 data sets of images I'm looking at here. One is the data set of windows containing pedestrians, and the other is a data set of just natural images. So windows containing just random windows in the world, with the caveat that they're actually random windows selected from images that could contain pedestrians. So sort of the negatives if you think of it in a detection setting. But it seems to hold for both. There's a little more variance for natural images, which I'll explain in a little bit. Okay, so far nothing interesting. Now let's say I downsample an image by a half. So this is the interesting case because now I'm actually losing frequencies. So first of all, let me ask the question. Now suppose that the large image actually was very smooth, so it didn't have any high frequencies. If I downsampled, what would the relationship be between h and h prime? Just from 1/2. Right. Very simple. I mean, it's just a reverse of the previous thing. But of course, now we're actually going to be we're going to be smoothing out information. So can we say anything about this relationship? Well, it turns out that it's actually 0.32. Why? And so I observed this fact empirically, and I went ahead and I took the whole collection of images, and it was in fact 0.32 for a lot of images with a small variance. This is a little bit of a surprising fact. Why is it 0.32? Why not some other number? Where is this coming from? And sort of this goes back to sort of this what I was talking about, this fractal nature of images. So basically, back in the 90s, people did a bunch of work that would take an ensemble of images at different scales, and they found that the statistics of those images were invariant to the scale at which they were taken. And this is what I was saying at the beginning. And in fact, that's not exactly true. The precise statement here is, okay, so let HQ just denote the gradient histogram over an image after it's been downsampled a factor of 2 to s. So that's just what we were looking at. So the precise statement here is the amount of energy lost in the downsampled image only depends on the relative scale of the pair of images and not the absolute scale. That's another way of saying that what's going on in an image is independent of the scale at which it was taken, right? And so basically what you get is, I'm just formalizing what I wrote up here. And again, this is all work done sort of in the 90s, and I'm just borrowing it here. Is that if you take the gradient histogram at a scale beta plus s, so downsampled by beta plus s, versus the image downsampled at beta, it'll be some function that only depends on s. It will not depend on beta. Okay, so it only depends on the relative scale of the images and not the absolute scale. And this only holds in the over averages. It may not hold for an individual image. And once you have h in this form, well, h actually has to have a exponential form in this case, and that's just some algebra to see that. So what we get is using sort of this very old, well, not very old, it's from the 90s, I shouldn't say that's very old, this fairly old knowledge of sort of the natural image statistics to make a statement about how gradients will behave when we downsample an image. Now, there's this parameter lambda, and so that's something we have to estimate experimentally. But we expect it to follow this law, and we expect to be able to just find this one value of lambda and be able to then predict how the features will change at a different scale. So we performed this experiment. So this is the same experiment I showed a few slides ago. This is this experiment where we got 0.32. But I repeated it for lots and lots of resampling values. So not just a value of 1/2, but also, so this is a log scale. So not just a value of 2 to the minus first, where we got 0.32, but also all these other values. And I plotted those points. These are the means. And lo and behold, linear fits works wonderfully to this data. It's really, really close. So we get some lambda out, and in fact, now we have the ability to predict how gradient will look in a downsampled image. Now, so this gets us most of where we want to be. There's going to be some error. The further away we look, the bigger that error will be. And so I'm not going to explain exactly what this number is, but basically the error of this approximation will get worse and worse. But now we have a way of performing this approximation. So let me show some concrete examples of that. So here's some typical computer vision images that we may work with, especially if we're computer vision researchers and publishing papers. So this is Leia, or Lena, I think. So this is the original image. On the right is the gradient magnitude. On the below is the gradient orientation. This is the upsampled version of Lena. Here's her gradient magnitude. And this is the downsampled version. So we have these 3 scales. This is the original one. And basically what we then did is computed a gradient histogram. And that's what you're seeing, these bars here. So just looking at the light blue, these are different orientations. So this is one orientation, second orientation, third orientation, and so on. And it's just computing the sum of the gradient magnitude at each orientation. And what I did basically is I did the same thing at the upsampled scale, but I knew it was supposed to have twice the gradient twice, so I just divided it by 2 and I plotted this histogram. And then I did the same thing for the downsampled one. And so what you see is basically the fit is extremely close. All 3 of these histograms are very, very similar. So we didn't actually, so basically what this is saying, if instead of downsampling and for this particular image and recomputing the histogram, we could have just used the histogram computed at this scale, and we'd have some little errors here. Okay, so this is so far all the statistics I was talking about previously were for an ensemble of images. This is an actual demonstration of how it works for an individual image. Here's another example. Here's a Colt 45, same thing. Here is a highly textured image. This is a Brodats texture, where it has lots and lots of high frequencies. This is not an image that's an example of an image typically found in the real world. And in fact, here, when you downsample it, you lose a ton because you're losing those frequencies. And in fact, the yellow bar here, which is the histogram computed at the lower scale, corrected for the scale change, is completely off. So in this image, if we were to apply this rule of predicting what the gradients would look like at a lower scale, we'd completely fail. Okay? The assumption is that these type of images are not that common. But the real proof, of course, is when we use this inside of a detection system, how does that affect performance? So, for these images sort of previously, like this one, the approximation holds quite well. For this one, it doesn't. Hopefully, most of the images we'll be encountering when we perform detection are of this form. So one thing, when I did that whole derivation, I was showing you all those gradients and whatnot. Actually, nowhere in that derivation that I used the fact that there were gradients. This whole idea that the image statistics are independent of scale, they performed those experiments back in the 90s, like Ruderman and Field and others. They performed for lots of different statistics. So it actually should hold for pretty much any image feature we may want to use. Now, that's not you can't analytically prove that statement or limit the type of features analytically that it may be applicable to. But in practice, any feature that people have tested back in the 90s and that we tested seems to follow this law. The only thing that changes is this lambda. So we use this on some local standard deviation features. And again, the lambda changed a little bit, but again, this beautiful linear fit some normalized gradient. So typically people don't use gradient, but do some nonlinear normalization in neighborhood. Same thing. This is actually Hog. This is the actual Hog code. So I got some Hog code by Dalal and Triggs and ran it on the Hog code, and again, it holds. So you could imagine testing this for other feature types, and until one does, you don't know for sure if the law will hold, but we have no reason to believe it wouldn't. And so, again, I'm using this observation inside of our own system to perform fast multiscale detection, but it should really be applicable to sort of any features you may compute and wish to approximate at a nearby scale. So we use this in our multiscale detector. So instead of creating an image pyramid, we actually can scale. So instead of actually having to downsample the image and recompute the gradients to perform detection of a bigger box, we can actually predict what the gradients would look like in a downsampled image. So we can do this all by just using the original scale image with the features computed over that. So that may be a little bit fuzzy right now. I don't want to go into like all the sort of technical algebraic details, but hopefully you can imagine how that process would be performed even if you don't know the details. So that's what we did. And basically what we found, and so again, this approximation degrades as the bigger your scale step is. Oh, actually I should say something. So because it degrades when you take a really big scale step, we actually ended up doing a hybrid approach. So normally you have a image pyramid that's finely sampled. We had an image pyramid that's very coarsely sampled. So every time you downsample, say, by a factor of 2 or downsample by a factor of 4, and then you do the detection for the scales nearby to that. So you can decouple the image pyramid from the pyramid at which you do the detections. So that's what we did. And so basically this here, I won't show too many curves here, but here we have, this is the actual scale step. So if it's not decoupled, so if your scale step is the same, so you do 2 to the 1/8 scale step as if the image pyramid and the detector pyramid. So this is the old way of doing it. This is the performance you get. So on the x-axis here is performance. These are 3 different curves at different false positive rates. So at this false positive rate, maybe you get about 90% detection rate on whatever particular measure this is. And then if you decouple the process of having the image pyramid and the classifier pyramid, so you have an image pyramid that you downsample by a factor of 2 to the first, so by a factor of 2 every time, you actually lose almost no performance. Not until you go to a downsampling factor of about 16 does it start to perform poorly. So you can so in practice we use the scale step of 1. So in practice we create this image pyramid of a factor of 2, but very, very little loss of performance. There's a lambda that we estimated empirically, and when we do the correction, we can use other lambdas, and it turns out that the lambda estimated empirically from the previous experiments is very near the optimal lambda, as one would hope, or otherwise there's something not quite right with our theory. And so we called this method at the time of publishing the fastest pedestrian detector in the West. You might have noticed some a theme throughout some of those slides. But anyway, so on these benchmarks, so channel features is sort of our baseline method. And the fastest pedestrian detector in the West, and they're sorted by performance. And so what you see basically is that our fastest pedestrian detector in the West is about 1% less accurate than the full-on image pyramid. And that's sort of where the proof lies, that this method of approximating features at other scales is really reasonable. And so we did this. This is the INRIA data. This is the USA data. This is some other data sets, and it's a very similar story. Usually our approximation is very, very close to the original detector. So how does this speed things up? So this is a speed versus performance curve. So speed on the x-axis, so you want to be sort of as fast as possible, and miss rate on the y-axis, you want to be as low as possible. So this is on the Caltech data set with 100 pixel and up. And so here is our baseline method. It worked at about 2 frames per second. And the new one goes to about 4 to 5 frames per second, depending on settings. So it's about a speed up of 10. I should say the Viola-Jones method here actually is a slow implementation because it actually doesn't use the classifier pyramid. So Viola-Jones would be faster. I mean, it's much simpler. It also is orders of magnitude less accurate, of course. But there's lots and lots of methods that work at 20, 40 seconds. we're at 5 frames per second. Similar story for when you actually go to detect smaller scale pedestrians. We lose a tiny bit of performance, but really move up in the speed category. So yeah, so that's our sort of our latest insight / contribution to sort of our detection system, and I'll be posting that paper on my website, and I think the camera is due in 2 weeks, so I won't drag my feet. Yeah, so is there any questions on that aspect? I'm almost done with the talk, don't worry. So yeah, like I said, I also am very interested in sort of the learning aspect of this, and yes?
Just a general question is, so all the data, all the images that you've shown me are daytime well-taken images. What happens, so your motivation was to detect pedestrians from a car. What happens at the nighttime when you have not so much?
Yeah, I think right now we're just hoping to do something in the daytime, and nighttime or when it's raining, or that's a little bit of a different story. Yeah, not quite there yet. Yes?
So you walk during the camera to fixed objects that looks like pedestrians coming toward you?
I'm sorry?
Suppose you keep the camera and you walk. And the stable objects look like pedestrians?
Oh, well, so we're actually not using any motion. So we're just using the appearance. So it wouldn't help or hurt us, any assumptions of that nature. But of course, if you're putting this into an overall system, that's the kind of things you'd want to be aware of. Yeah. Yes?
So the speedup that you mentioned, it's basically affecting the time taken to compute features, hog features.
Yes. Yes.
But the number of boxes that are being evaluated...
It does not change at all.
So you mean to say, like, it's just surprising. I thought like the hog feature extraction code that's available online, like either at Pedro's website or Dalal's website, is like reasonably fast.
It is reasonably fast for single scale.
You're improving upon that. The time.
Yeah, because so basically now, so that is reasonably fast. So you can do real-time single-scale detection with that code. But when you create the image pyramid and compute the features at every pyramid, it's a fine image pyramid because let's say you have 8 scales per octave. That's when it gets quite slow. So that's what we're saving on. It's the same code. Let's say you're using hog features. We're not using hog features. We have our own. But instead of having to compute it at every scale, like 8 times per octave, you only compute it once. So that's the speed up. And in fact, because we're using sort of this boosting with cascades and all that, the detector itself, the evaluation of the window, was quite fast. And the bottleneck was the computation of the features, and that's what we've alleviated.
Because there's like complementary set of work which says feature extraction is fast, but the number of windows to be evaluated is huge. That's the branch and bound and other works.
Right. I mean, so they are orthogonal issues. So this doesn't address at all the number of windows. So, I mean, one of the things is if you have boosting with cascades, actually some of those claims about the evaluation of the windows being really slow may not hold as much as if, say, you're using like a kernel RBF or something like that, where actually evaluation of each window, even after you have the features, is quite slow.
So I have a question.
Yeah.
So you don't do any explicit occlusion modeling, right, in your work, but
Right.
I'm really surprised that you get such good results, because that's where I thought it would be equivalent for like part-based methods.
Yeah.
Because, if you take like Deva's work, they kind of...
Yeah, the problem is that the current part-based models don't explicitly model occlusion. So if you just have a missing part, it's a lower score.
There's also some other work where you can reason about the missing parts.
Yeah, so there's yeah. So I think methods like that would definitely be the right way to go. I think that there just wasn't a compelling data set before to really, so you could simulate data sets like that. Like there was an ICCV paper last year where they had this hog LBP thing where they tried to estimate what part of the pedestrians are occlusions and all that, but they had to simulate the data. And so it's just not as convincing as, if you actually have a real data set, which we do now, but we actually haven't performed any experiments along those lines. Yeah, but that's exactly the right type of approach I'd advocate. So let me say a little bit more what I think sort of the future work is in pedestrian detection, or where I see sort of the field going. And the way I see it is really that there's two separate problems. There's the low resolution domain, and then there's the high resolution domain. So in the low resolution domain, this is an image from Antonio Torralba at MIT. A lot of you have probably seen this where, so what does this look like? If you've seen this demo before, don't say a car. And what does this look like? Oh man, it actually, Antonio took, and these are the identical pixel values underneath. And so the only reason you know this is a car versus a person is based on context, because if you were to look in a local window, they're exactly the same. And so I think right now a lot of the work in pedestrian detection is saying there's only so much we're going to extract from the pixels, and using sort of the surrounding information, so the context, temporal consistency, kind of whole system performance. Like if you know you're in a car, you can exploit that type of information. And you know, this helps a lot in the low resolution domain. It also helps a lot in the high resolution domain just because our detectors aren't that good. So even if you can clearly tell it's a person just from the pixels, our detectors can't do that. So in some sense, all of pedestrian detection is in this domain right now. And probably all of object detection, just because our object detectors are not that great. But really what I would argue is that in the high resolution domain, which, you know, and in some ways the whole Caltech pedestrian data set and that whole application with those resolution cameras really argue that this is where you want to be. But I'd say that there's this other domain which is just as interesting, which is a high resolution domain, where if I took a Porsche, let's say, and put it here covering up this guy, at this resolution, you would not think that's a person just because of the context. You'd know that'd be a car right there, right? So I would argue that in this high resolution, you can really just take the local window and extract the information from that and really try to do a lot better. And that's where I think sort of the part-based models, you could use segmentation, richer features, you really have a lot more pixel data just directly coming from that region. And so much of my work sort of over the past year or two, which has been motivated by the Caltech data set, has been sort of simplified in looking at the low resolution domain. We weren't using context. I have some students working on that this summer. But it limited the type of approaches that were really successful in that domain. And I think this is sort of where, and I don't know if there's any ideal data sets for this, but this is sort of a very interesting problem, which is sort of where I want to move next. Where you really get to do more interesting things in terms of extracting information from the local window on which you're trying to make a decision. Yeah, so that concludes my talk. If there's any questions. Yes?
Looking at the low picture below, how much of the detection goes bad or good depending on the local de facto dress code? Like the man on the left with his multicolored stuff is almost a camouflage uniform. Right.
Well, so I would say that the current detectors probably wouldn't mess it up because they're not even. They would downsample this first, and you really wouldn't even be. You would discard those details that may confuse you. But I think if you actually wanted to do detection at this resolution, that's the kind of things you'd start thinking about. Yep. Yes?
How accurately can you estimate the size of a crowd?
Yeah, so I mean, one place where sort of all of these detectors have a hard time, I mean, these are all sliding window, they don't have any reasoning about if you have a couple people very close to each other, which parts come from which person, or anything of that nature. I mean, they're just these monolithic classifiers. So that's definitely sort of a area where things go bad. And then, you know, we have these heuristics afterwards of non-maximal suppression where you have all these detections and you're trying to actually say how many people there are. And that's definitely a pretty challenging. I mean, at this separation, you're still okay. But once people start overlapping, basically your detectors give you that there's people there. You get sort of it's firing everywhere, but you have no idea, you know, what's actually going on in the image. Yeah. Okay, cool. Thank you.